Let's go for it. Let's do it.
Hello, hello. Are you all ready? Yes? Yay. I like the enthusiasm. Okay, I'm gonna talk now. Hello, hi. Good afternoon. Thanks for listening. It's my absolute pleasure to introduce Andrea. Andrea, I can't tell your last name.
It's Bajcsy, like Tai Chi, the martial art.
Dr. Andrea Bajcsy here from CMU Robotics Institute. She's one of us with us today. She's the head of Intent Robotics Lab. She's a very new faculty, but she has already done enough.
Is this my permission for tenure already?
No, that's if I had power, then I would give it to myself. So, okay, you can read her bio. It's everywhere. She's amazing. She's very successful. She won the TRO Best Paper Award, I think, and then the NSF Graduate Fellowship way back then when it was a thing. And also worked at NVIDIA, making really safe cars run around, drive around, right? It's amazing. We all know about this. I just want to say something else. Beyond all of this, all these CV highlights, Andrea is one of the most insightful and thoughtful people I get a chance to know. She brings both intellectual rigor and also this really sincere warmth to every conversation that I had with her so far. So if you're at CMU, you are very lucky to have her here. Please use this chance to not only interact with your advisors, also interact with other people like Andrea here. Okay, please join me in welcoming Andrea.
Thank you so much for that warm introduction. Yeah, it's really such a pleasure to give talks at your home institution. I see so many familiar faces. I also see a lot of new people. So let's just jump right into it. All right, so the key thing that I think is so exciting about being a roboticist today is that for the first time, robots are actually kind of useful. Now, they're not perfect, but I never thought when I started my PhD almost 10 years ago that I could go to San Francisco and take a fully self-driving car all around San Francisco. I did that just last week. It's amazing. Okay, same deal. People are actually using these Skydio drones to do bridge inspections. We're starting to see progress from nothing to something in manipulation. The time to get involved in this is so much easier for anyone. And task planning is getting easier and easier as we start thinking about the use of language models in the loop too. So it's a really exciting time to be a roboticist. At the same time, it is precisely these increased capabilities and deployment that have got people worried about safety. I'm sure everyone followed the trials and tribulations of Cruise. Companies like DeepMind are really worried about safety, for example, for their LLM models that interact with people. They have entire divisions for this. And the prior administration had an entire executive order on the reliable deployment of AI-enabled systems that you see shown here. The thing is, though, that we think about the problem of safety for robotics that are getting deployed out in the open world, what safety really means is actually quite a nuanced concept. So consider this seemingly simple definition of safety that you might encounter in autonomous driving, which is collision avoidance. And if you look at this example, here's a Tesla self-driving car on the Bay Bridge that decides to do a hard brake on the Bay Bridge. Okay, this causes a multi-car pileup in the middle of the road. I was actually in San Francisco during this time. This ruined my plans to go downtown. Okay, what I like about this example, though, is that we often think, oh, well, to avoid collisions, just stop. Okay, but stopping is precisely what caused that safety violation here. So even if the safety spec seems simple, even if I know what failure is, getting safe decisions is very, very hard, okay, and very, very context dependent. However, safety is much more than just collision avoidance in the open world. consider on the right-hand side this fantastic work from Professor Ani Majumdar's group and DeepMind, where they were using a large language model as a task planner for this robot. Okay, and here you see the top most likely generations of what the task planner suggests to do. And this paper made a really important statement, a really important contribution, which said that robots shouldn't just do the most likely thing, because in fact there are two very likely task plans here. When there's uncertainty like this, the robot should ask for help. This is an important capability for a safe robot. What I find exciting, though, about this example is if you look at the top two generations, they also tell us something else. They tell us, wait, I never want a robot to put metal in the microwave. I never want a robot to microwave plastic. These are bad things that should not even be suggested in the first place. Finally, I like to look at this Roomba, which literally broke free from its closed world. It's out in the open world. And this Roomba, for whatever reason, struggles to understand the consequences of being too close to this pool edge. It does not understand that it's dangerous to get into that water. Okay. So the key thing I'm really, really interested in is how do we generalize what we mean by safety in robotics? And for me, from a technical perspective, I come from control. So I like to think about this from the perspective of robust control. And these methods have very general principles. Here are the two principles that underlie these techniques. Okay, first are dynamic games. Okay, these models let us think about the closed loop interaction between the robot and its environment or other agents. Secondly, these techniques specify safety very generally. Safety constraints are just arbitrary sets in state space. They don't have to be necessarily convex. Just give me this representation. I can tell you whether or not I can satisfy this. And over the past decades, this type of safety has been steadily making progress. Here are just a few examples of some nice videos that I found of works that are progressively pushing these techniques into higher dimensional systems and more complicated settings. And we already discussed how what's really nice about this paradigm are these feedback loops. Another thing I really like about these types of tools is that they really tightly couple the detection of unsafe events with mitigation strategies. My robot knows what to do when something weird is happening. Okay, the problem though, the thing that has been holding us back in this community is that this very general mathematical framework has been limited to hand-designed state spaces and hand-designed representations of failure. And any student who has worked on these types of problems will know that it is a very arduous, highly expert-trained problem to do this, to write down the state space and write down failure. At the same time, generative models, have been growing in parallel. Now, these models have been able to learn low-dimensional patterns about the world from really complex high-dimensional data, like human behavior, image observations, and they can increasingly build more and more kind of common sense understanding of the world. Now, the strengths of these models are that their latent representations help us capture aspects of the world that are very hard to write down by hand as an engineer. They're also easier to guide, I'd argue, with human feedback. I'm sure all of you have given a thumbs up, thumbs down to ChatGPT. Even if you yourself don't understand how that model works, it can be guided. The problem is that when we typically think about safety in this context, we're typically thinking about something like anomaly detection or uncertainty quantification. Okay. So what do I mean by this? Here's an example from this paper where you can actually query an LLM to look at this scene of the Cybertruck with this traffic pole on the back of it, and the LLM will tell you, wow, that's pretty weird. Haven't seen that before. Okay, but now what does the robot do? Does it pull aside the road? Does it do a hard brake? I don't know. And so my hypothesis is that we can systematically unite the recent advances in these types of models with classical formulations of safety and control to start generalizing safe robot decision-making to increasingly open world environments. And that's what we're going to be talking about today. Now, my group has done a bunch of recent work on this. We've been thinking really hard about this. I do not have time to go into everyone's projects in detail. I just want to flash some of their work here. We've done stuff on uncertainty quantification, on system-level anomaly detection, on safe decision-making around people and in new environments. But for the sake of today, I just want to zoom in and talk a little bit about some foundations, so we all can speak the same mathematical language and think about safety in the same way, and then talk about 2 frontier papers we just released on arXiv, because everyone wants to know the freshest stuff. Okay. That's what we're going to talk about today. All right, let's first have a common understanding of how we think about safety. Let's talk about some foundations. And I'm going to start with this simple motivational example from some of my old work during my PhD. Okay, so here is this robot. It's navigating in this environment. And it's using, in this case, a vision-based planner. That's on the right-hand side, you see what the robot sees. And it's trying to navigate through this unknown environment to reach some goal. As you can tell, though, this planner is kind of optimistic, and it ends up having the robot collide with this chair because it takes too tight of a turn. And so I want to use the vision-based model. It's actually quite good at navigating through this unknown environment. But I want to somehow minimally modify it to make sure it doesn't make these extreme bad decisions, on these like corner cases. Okay, how do we do this without touching the base policy? I don't really want to make any assumptions about it. The idea from control systems that we're going to be exploring today is something called safety filtering. So these are essentially wrappers. They're policy agnostic wrappers you put around any base model you want. This model is going to be detecting any unsafe action generations the base model is proposing. Okay, and it's going to minimally modify those generations to ensure that the present actions don't result in future failures. Now let's understand how to construct these kind of from first principles with that simple example again. There are 4 key ingredients that we need to do safety analysis. The first, we know it, we love it, a state space. In this particular example, you can think of this as quite simple. Okay, XY position, velocity, heading. Now my state evolves over time. This is just dynamics. I can spend time writing down a first principle model. It can be an ODE, it can be a discrete time model. It could even be, in theory, calls to a simulator. But I need to know how it evolves. And if you notice here, this dynamics model evolves based on not just the robot's input, U, but also some exogenous input, D. This is the grounding and robust control I was mentioning before, which basically says things that we are uncertain about, we need to model and then be robust to. So typically an ingredient here, we need some opponent model. It can be, for example, other agents that are explicitly adversarially attacking us. It can be hard to model friction or external forces, anything that we might want to protect against to be robust. Last, but certainly not least, we need our failure specification. In this case, our failure set is quite simple to write down if we know the map of the environment. It's just the obstacles. So let me show you that obstacle map here top down, just in the position space. And this is our failure set, in other words, our safety specification. So let's cook up this safety filter. And we're going to use a particular tool here called Hamilton-Jacobi reachability to synthesize the set of states from which my robot is doomed to enter those failure states, no matter what it's going to try to do. The way we do this in reachability is we're going to encode our failure set in a functional form via the sign distance function L of x. Okay, if it's less than 0, you're in failure. If it's greater than 0, you're safe. We now want to know, for any initial state of the system, does there exist an action the robot can take so that it steers clear of failure? And this must be true in the robust case, even if there are these adversarial perturbations to your system. Right? So formally, this is a safety critical game that you can write down, whose value you can write down like this. And the most important high-level takeaway about this equation is that essentially here, this value function is remembering. It's remembering the closest the system ever got to failure, despite the robot's best effort to prevent failure. Now, thanks to decades of progress, we can solve this safety game today with a myriad of techniques, from grid-based solvers in low dimensions to adversarial RL or self-supervised learning in higher dimensions. And here I'm showing you this computation in real time for this low dimensional example. Let's play it one more time. You see that value function computing, and you see the boundary of the failure states retracting. It's getting bigger. That's indicating to us there are situations in which my system is doomed. Okay, let's take a look at that. So here I'm showing you the slice of the value function where the value is equal to 0. That's what that red boundary looks like here. What we have computed here is we have, under the hood, co-optimized a safety policy that tells us how to stay far away from failure, and a safe set, which is just the super zero level set of our value function. That's going to be our monitor. Tells us if we're doomed or not. Here are just a few visualizations. I'm just showing you states all at the same heading, so the robot is facing upwards, different states in PX, PY. And I'm showing you the optimal safety policy. And it's intuitive, right? It's saying, oh, push me away from the obstacle here, push me away from the obstacle here. But there are certain states at which you might be doomed. You have to start taking that recourse much, much earlier than exactly at the boundary of the obstacle. How you do safety filtering, there are many ways to do this. I'm going to show you the simplest paradigm. Anytime you're inside of the safe set, your value function is greater than 0, you're good to go. Just apply whatever policy you want. If you get to the boundary, to the 0 level set, that means that you are almost at the point of no return. At the boundary, you have to start applying your safety controller to keep you inside of the safe set. Otherwise, once you cross that threshold, you're doomed. There's many filtering works. There's many smarter ways to design this. Please check out these surveys for more details. Let's see this in action. This is the same example from before. And here, the boundary you're going to see in the top right is that safety filter wrapped around that vision-based policy you saw before. Okay, it's being updated actually here online based on new measurements it's getting from its mapping algorithm. Ultimately, the safety filter is detecting when the vision-based policy is trying to steer it really aggressively to cut those corners, and it's overriding those commands to nudge the robot into the safe set. Over time, when you put these two pieces together, the base policy and the safety filter, the robot can make its way towards its goal location safely. Okay, good. So the thing that we need to think about, though, now is in all these problems we've been kind of talking about so far, and in fact, the majority of safety critical control, the way that we represent failure is collision avoidance. I'm just showing you snapshots of some of my work and my close collaborators where this is the kind of stuff you're representing: collision with agents, collision with objects, collisions with the ground. The actual types of safety failures I want to talk about, though, are these. I want to talk about spilling. I want to talk about braking. I want to talk about tearing. So what's holding us back? I think the best way to understand what's holding us back is go back to our 4 core ingredients for safety. Let's ground ourselves in this example, where there's a robot manipulator who's going to be picking up this open bag of Skittles. Whoops. Okay, spilling has happened. Now it's time for a pop quiz for all of you. What's the state space?
Purple, orange, pink, and yellow.
Maybe? Maybe. What are other parts of your state you might need?
The center of mass of the
Oh,
particles.
of the particles? Okay, center of mass of the particle, sure. Maybe also their position, right? What else? What else?
Position, shape of the box.
Of the box? There's no box. Which box?
I'm sorry, the Skittles I thought was the box.
The Skittles bag, you mean?
Bag.
Ah, yeah. Okay, what does it mean to represent the state of a bag?
Mesh.
Yeah, maybe mesh. Yeah, exactly. Okay, good. Okay, so it's getting kind of interesting, right? We also haven't even talked about the robot state, by the way, right, or the table or any of these things. Okay, what about dynamics? What's the dynamics of the system? Assuming we cram all of this state we just described, color, okay, we put mesh, we put center of mass, we put all this in our state. What are the dynamics? Yeah.
Gravity?
The gravity will affect it for sure, yeah. Anyone have any thoughts on how you model like particles interacting? There's like a word for this.
Contacts between all particles.
Yeah. Actually, if you go talk to, a lot of the numerical mathematicians or the applied mathematicians, they'll tell you, ooh, I need to start doing something like a, fluid dynamics simulation, right? To think about how the particles interact. Okay, that's a high fidelity model of that dynamical system. Okay, what about the bag though? Man, like what is the dynamics of a mesh? That's also really tricky. And then what's the dynamics of color? Technically those Skittles could have, they could kind of start degrading over time. Skittles on the inside are white. Maybe that matters for the task, I don't know. This is very hard. What is failure? What is our failure set? You look like you're gonna.
Distance between any Skittle and the table is small.
Perfect. Skittles on the table. Okay, so you guys are hopefully on board with me that this seems really challenging, but this is what I ultimately want. Okay, so if we go back to this question, we might seem to be struggling here a little bit. But the fundamental thing that we need to overcome here is we said to ourselves, well, maybe to reason about safety, I need to go beyond hand designing all of these models. I need to go beyond hand designing the state, the dynamics, and the failure. That's just not really going to scale here. And so what we're going to do now is we're going to take a really big leap from those control system safety foundations to our first frontier. We're going to talk about latent space safety. Okay, so again, it might seem like all hope is lost, but there is one nice thing about a problem. We can all agree that if I show you observations like this, failure is observable. If I show you this image of what the robot sees, you can say, yep, a spill is happening. This is good. This means there's hope because if I can observe something, maybe I can control it. The problem is, it's really hard to know how to predict if the robot's actions are going to result in this outcome. So our idea to tackle these two problems is essentially to start doing safe control synthesis directly in the latent space of a generative world model. Now, mathematically, before we were operating like this, now we are operating like this. Okay? X has transformed into Z. Z is the canonical representation of a latent state. And you guys might say, wow, Andrea, this looks so obvious. Like, you just changed the variable. But let's actually unpack this a little bit more. It's not necessarily trivial. So just to recall, this is what we had to do before. This was our state representation, failure, and our dynamics. Now when we lift this problem to the latent space of the generative model, our state is going to be some embedding of like a sequence up to a sequence of observations. Our failure now becomes a classification problem on the latent space that we have learned. And our dynamics are this latent world model that I'm about to go into details with. Okay? Yes?
Why did you change U to A?
Because in this paper we use A as a notation. Oh, okay. Thank you for that point. U and A are equivalent here. A is popular in AI literature. U is popular in control literature. I will sometimes switch those two, but they are the same. Thank you for that comment. I'll make it consistent in the future. All right, let's get into it. Let's talk about the construction of our state space and our world model. Okay? Here's how we do latent safety analysis. We start by building our world model, where we assume access to a data set of observation action pairs, like I show you here. Okay, the observations are proprioception, and the wrist and the third-person RGB camera inputs. Our model is going to map all of these observations, okay, to some posterior latent state. I'm noting this as ZT here. This is what I mean when I say latent state throughout the talk. Okay. Then our dynamics model is going to take all those actions that are in the data set, that encoded observation that we just got, and it's going to try to predict how the current latent state is going to evolve to the next one. And since we know the true next observation in our data set, we can train this in a variety of ways. You can do reconstruction, you can do teacher forcing. There are many, many techniques here for doing this training. And I don't want to claim that we invented this. We did not. There are wonderful, wonderful works, for example, from the model-based RL community, from the generative modeling community, that have spent a lot of time thinking about the design of these models. And so you should please check out these papers. These are the 2 papers that we specifically use throughout this work. Okay, so we have our world model. We have tackled the first 2 hard ingredients of safety, but what is failure? How do we get that? How do we represent it? Well, recall how I said that our failures have to be observable from the sensors. Okay? So now what I can do is I can have all of you, for example, look at this data, and you can tell me, yep, left one looks pretty good, right one looks pretty bad. You can give me those labels. I can use this to once again take my world model's encoder, reduce the dimensionality here, and then train on top of this a classifier which will tell me, or it'll try to predict for any new z, is it good or bad? And here when we do training, our loss is penalizing essentially actual failure states from being labeled as positive and vice versa. In reachability language, in our optimal control framework language, we essentially have this implicit failure set encoded inside of our classifier, right? Anytime the classifier gives me less than 0, I know I'm doomed. This is great. We have basically all our ingredients. And so let's talk about what our safety critical control problem is going to be. This is our latent safety problem. If you notice, it operates on the latent space of the world model. Everything's in Z space now. So I'm drawing here what that world model abstractly looks like. That L of theta function is our classifier. It's telling us this region of our latent space is bad. In fact, if I decoded one of these latent states, you might see something like this. This is an imagined Skittle spill. If I take any initial state in this world model, my optimization is essentially thinking about the robot's best effort to avoid these failures, but all in the imagination, no additional rollouts. So you can think of the world model as a simulator now. And this optimization is saying, given the robot's best effort to avoid failure, how close does the robot come to failing? Now, to solve this problem more tractably than forward simulation, we can derive the latent safety Bellman equation that I show you here. And if we were to solve this value function perfectly, we would see this latent unsafe set growing over time, encoded as all of the states where the value is less than 0. And what's really cool here is that you'll discover situations like this. If the robot has come to a point where it's pulling up on the bag so high, no matter what it does, no matter if it tilts or twists, because those skittles are all in there and they have momentum, they're going to fall out. You're doomed already. So you can never reach some height when you're pulling up, otherwise it's over. The last but important thing I want to mention is that this computation operates on still a fairly high dimensional latent state. Z here in some of our experiments is 512 dimensional. Now I want to be very, very clear. This is better than the raw observation space. If I give you two camera images, right, wrist and third person, 3 channels, 128 by 128, it's a 98,000 dimensional problem. Okay, so 512 is better than that, but still too high for an exact grid-based solution. So what we end up doing is approximating this via doing reinforcement learning in that imagination, fitting a neural value function essentially on top of this. Okay, and this backup is not something that we introduced. You can check it out here. Okay, but this backup lets us use off-the-shelf RL tools. Just download them from the internet. All right, we do the synthesis. We get our 2 quantities out, our safety monitor, safety policy. Let's check out how it works at deployment time. Here's the context. The robot gets its observations and codes them. It follows whatever task policy it wants. Okay, so here we see us moving to the latent space. At some point, there reaches a point where, soon I will reach the point of no return. I need to override this control with my safety filter. Okay, and so what we do is we override the base policy's actions with our safe control actions. Now, a quick sanity check we did first is before actually solving this high dimensional Skittles problem, we actually wanted to test something where we had access to the ground truth safe set to really sanity check, does this work? So we said, how close does latent safety get to privilege safety? A canonical safe control problem looks something like this. You have a Dubin's car. It has a fixed linear velocity. It can't slow down, but it can just turn. The privileged failure set is just distance to this circle here. Our latent model takes as input image observations of the entire scene plus the heading of the robot. Our data set is 2,000 random motions in the environment. Our world model is an off-the-shelf dreamer model. This is a recurrent state space model. And our failure classifier, L of theta, is trained on the same data as our world model here. OK, what I'm showing you here, leftmost plot is the failure. Ground truth failure, it's that circle. The center and the right are slices of the backwards, of the unsafe set at two different headings of the robot, facing to the right and facing up. This is the best you could ever do. So this is with like a privilege solver, really, really fine discretization, everything's good. Then what we did was we took our privileged state, privileged dynamics model, and we did an RL-based approximation here. Okay, so the only error that comes here is from RL, not from the models. Okay, here you see the F1 score. This is kind of like a binary classification quality metric here. 1 is the best you could ever do. So it's very good. This is what latent safety gives us. So the failure classifier is a little more conservative. There's some error showing up in the unsafe set, but the F score is still really, really high. And I want to really stress here that I'm showing you these low dimensional states for verification because, like, we have the privileged access here because it's so low dimensional. But actually what the latent safety filter sees are these direct observations. We just know they're mapping to the privileged state perfectly in this example. So after we saw the sanity check, we said, this is great. Let's scale up to visual manipulation. We're going to look at this visual manipulation task where the robot has to pick up that green block, but it should not have those red blocks fall down. Now, what's nice about this is that a stakeholder can easily identify these things, right? Like if I showed you the rightmost image, you're like, that's bad. Leftmost image, that's good. But interestingly, our failure spec says that the center image, okay, is also good. And that's because we're not considering a collision avoidance spec. The robot can touch, tilt, push, interact with those red blocks as long as they do not fall down. So let me show you that initial video, but in like frame by frame. This is an unsafe rollout. We saw those blocks fall. I'm going to show you over time what our failure classifier and our safety monitor says for each of these observations in the trajectory. So we start off at the beginning of the world. Both of our systems say, yeah, life is good. Life is still good. Life starts to get bad. Okay? Our safety filter here actually says that at this point, the robot has come in to grab that green block so quickly. It has touched those red blocks so fast that they are doomed to fall down in the near future. And that's why here you see that V shield already is saying, nope, you're in the 0 level set, or the sub-0 level set. This continues to be true. The blocks haven't fallen down yet, so our failure classifier isn't firing, but we're already doomed. It's over. Finally, when you get to the actual failure condition, our failure classifier correctly says, OK, the failure has now actually happened. This is that gap that we saw in the earlier examples, too. If we put our safety around a base policy, here's what's going to happen. So these are two different conditions of where the blocks are relative to the robot. Anytime the green border is lighting up, that means that the safety filter is active. And here you see that those blocks are wiggling around. They're wiggling around, but they never fall down when we safety filter the base policy. We also we have some quantitative results associated with these qualitative ones as well. Here, our nominal policy was a dreamer policy trained on the same world model where it has soft constraints understanding. We also compared to a constrained MDP formulation 2 off the shelf. And we basically see that across 50 initial conditions of the blocks randomly initialized in the world, we found that our latent safety filter helps the dreamer-based policy succeed while minimizing those constraint violations. OK, but let's all talk about the hardware. That's what we really want to see. All right, so let's go back to our Skittles example and close the loop here. What I'm going to show you first is my student Ken. He's just going to be directly teleoperating this robot. And he decides to accidentally pick up this Skittles bag from the bottom. So we see that failure happening here. Now let me show you what happens when we turn the safety filter on. On the left-hand side, Ken is going to grab the Skittles from the top. The filter is not active. It says do whatever you need. This is safe. He's going to grab the bottom now, but instead of pulling up, he's going to shake side to side. Most of the time, the filter is not on. Occasionally, you see that green boundary show up. The filter is slowing him down. Because if he goes too fast, the Skittles are going to come out. Finally, he tries to take that unsafe grasp and pull up, and you're going to see solid green. You cannot do that. And I want to show you a contiguous shot of this. You can come down to my lab and play with this too. In this contiguous shot, you're going to see the value function plotted on the lower right-hand side. And so the value is positive. It's safe as long as his actions are also safe, like picking up from the tip. As he starts to reach the bottom and he's going to start shaking, the value is going to dip. This is the predicted value of the next state given the robot would execute his actual teleop actions. So you see that dip? Okay, now he's going to try to pull up from the bottom really hard. The value is going to dip a lot. It's going to say, do not do this. If you keep doing this, you will be doomed. And so it's overriding him. All right, so please check out this paper for more details. We also wrap the same exact safety filter around a diffusion policy too. And we show that it consistently helps that diffusion policy that's only trained on safe demos stay safe. But what I want to now talk about is one part of this pipeline that is still kind of frustrating. Okay, so take a look at this. Remember how I said safety specification is now a classification problem? And we had to label these images, right? In fact, here is Ken, okay, working really hard. He's labeling that data. Now, I would argue that labeling the data is easier than writing down a very fancy mathematical function. So that's good, but that's still pretty arduous. Okay, so how can we maybe alleviate this burden? Maybe use some knowledge in pre-trained models to generalize the detection of failure. And this is where we're going to take our final deep dive into what we're calling VLM-in-the-loop policy steering. All right, so same robot, different context. This robot is now trying to perform this task of picking up this mug and serving this cup of water to a guest. It's using the same exact observations as you saw before, but the base policy we're going to be studying now is a diffusion model. Okay, so this low-level model is really quite nice at looking at a bunch of expert demos. There are many ways to do this task, picking it up by the lip, the interior, all these kinds of things, and learning that distribution. The robot then, to make a decision, is going to sample from this model. Here are just 3 example samples from each of these modes in that data set. The problem is that not all sampled actions result in the same task performance. So for instance, if I happen to sample this one, life would be actually quite good because this robot grabs the handle. That's a pretty appropriate way to serve a guest a cup of water. But if I sampled this other mode, the robot doesn't fail at the task, but it puts its fingers inside of my cup. Okay, I don't like that. I don't want my robot contaminating my cup of juice. Finally, there's one other sample here that when the robot actually executes, it totally fails at the task. Okay. So the base policy isn't terrible. We saw some good generations. But what we really need to do is we need to verify that the robot's sampled action plans are going to actually result in good outcomes. How do we write this down? How do we formulate this problem? We can think of this problem of policy steering as essentially a model predictive control problem. It looks something like this. You take a bunch of samples from your base model. In this case, I'm showing you just 3. Okay, so these are the 3 samples. And now the trick is that I only have actions. But actions don't tell me outcomes, right? For outcomes, I need state, basically. But in general, what you could do is you could say, maybe I have some video prediction model or something, and I think about every future observation I could ever get conditioned on this action sequence I got. And then for any given imagined observation, I need to evaluate it. I need to do that verification. I pass this into, for example, some reward function and knows about the task context and says, yeah, this is a good or a bad imagination of outcomes. Yes, please.
These actions are in the ambient space or in the latent space?
These are delta end effector,
Okay. So
like dx, dy, and z. All right. The question is, how do we actually solve this? It looks really hard. And so what we're going to do is we're going to say the following. We're going to say, thinking about those outcomes, that's something we've already seen before. We can use that world model once again to reason about those outcomes. But now what we're going to do is to, minimize my students' efforts. We're going to try to use a pre-trained model for verification. This pre-trained model here is going to be our VLM. But the key trick is we're going to get the VLM to reason directly on those latent states. So you can see it consumes the z vector. And this should help us unlock the VLM's kind of pre-trained reasoning knowledge to score these generations, but in a very grounded way that's actually linked to the actual embodied outcomes. Let's just go step by step through the process. So as we saw before, here are the observations. We love our world model graphic. We're going to encode these observations into our latent state. For each action trajectory that we sample from our base model, we forward simulate the latent state trajectory. Here I'm showing you reconstructions of those imaginations just so you build some intuition. These are not used for actual reasoning. You can see the different outcomes the model is figuring out. Oh yeah, okay, the cup has fallen down, the cup has been grabbed by the lip, the cup has been grabbed by the handle. We only take those latent states, and now we're going to pass them to the VLM for verification. We use Llama 3.2 11B Vision Instruct. It's an open source VLM you can play with. And what we do is to get it to reason directly on the latent states, we pose a fine-tuning problem where basically we get the VLM to reason directly on that different representation of the visual world by posing a visual question answering task. This is a very common task a lot of these models are actually trained to think about. But it helps the model decode the latent state into its representation that's native, text. So here is how we're going to actually do the verification, where we give the VLM a prompt about the general task at hand here, grabbing the cup from the table. Then we ask that VLM to decode each of these latent states into a textual behavior narration. So the VLM says, okay, the thing that's happening in Z1 is the robot's attempting to grab the cup by the handle. In the second one, it's attempting to grab by the interior, so on and so forth. Now, given a particular task description or task context here, like serve the cup of water to the guest, we have the VLM, the same one, we call it again, and we say, given these descriptions that you generated in this task context, which one is the best? Okay, so the model says, well, mode 1 is pretty good because you're not spilling and you're not contaminating. So in essence, the VLM here is solving that argmax in our model predictive control problem. Let's see it in action. So, unsurprisingly, serving the cup of water to the guest, the VLM says you should be picking up by the handle. But the nice part is because of the pre-trained model's capabilities, you can change the task description and it'll still be able to steer. So you can tell it a novel task description like, hey, wait, there's oil on the handle. And the robot will say, okay, I should pick up by the interior. This also works for other kinds of problems. For example, this hard to manipulate bag of chips here. If you tell it avoid crushing the contents inside, the robot will choose to pick up by the edge. But if you tell it, hey, grab it really stably, the robot grabs it by the interior here. Okay, so it's going to go ahead and grab it by the inside here. I'm just going to flash some quick quantitative results on the policy steering performance. The main thing I'm going to show you, forewarn is our method that has the world model plus VLM. VLM act as a baseline where we directly fine-tune exactly the same VLM to just end-to-end go from observations, actions, to the behavior descriptions. So it uses no world model in the loop. And you see, quantitatively over 10 trials on hardware, the success rate is much worse for VLM act compared to our method that uses that grounded world model for reasoning about the fine-grained details of embodiment. And that's specifically what we see here if we take a deeper look. So if I show you these privileged observations of the cup and the bag task, and I ask each model to narrate these, our model narrates them correctly. It says, oh, the robot is seizing the cup through the interior. Oh, the robot is grabbing the chip bag in the middle. It knows these fine-grained details. But VLM act, with the same exact data set size, we have a small data set here, okay, is going to struggle. It says, oh, it's grabbing it by the handle, it's grabbing it by the corner. It's struggling to pick up those fine-grained details. We have many, many more experiments and ablations, so please check out the paper for these. But I think this is an exciting step towards trying to generalize the detection of hard to write down failures. Really, really hard to specify failures. Okay, with that, we have reached the end of our deep dive in our journey along this unification. There is so much more to be done. We are just scratching the surface of this unification. So if any of you are curious or interested, please come talk to me or my students. You should definitely talk to my students. They're the real experts. And I want to just explicitly shout out the students whose work I was advertising today, either at the big summary slide or the specifics works we did a deep dive on. So please go and talk to them. With that, thank you very much. Happy to take questions.
Yeah, it's a really good talk. Thank you, Andrea. Questions about generalizations. So the high-level question is like, how hard is generalization safe to work? But the low-level question is, in the first work, how well does the L theta function, the specificity function, generalize? Does it generalize to M&M, trained from Skittles?
To M&M.
Yeah. And the second one, how well does the VLM generalize?
Yeah,
generalize to different cups and different, yeah.
So we're running those tests right now. So I don't know empirically yet. I think it really depends on how much priors or how many data you put into the overall training pipeline. So here we're operating on really, really small data regimes. And so the boundaries of where you generalize is probably not that strong. But we're doing rigorous tests right now to actually check this. As you can tell, RSS was just recent, so we haven't done all of these stress tests.
How do you have scalable safety? Like in the sense that, like, do you think data is all we need, or we need to develop something else to make it scalable?
Maybe my philosophy is something like this. The data that we used in this project is what companies are anyways collecting. Every time you do an evaluation, you generate this data. Anytime you get your demonstrators to give you data, you're generating anyways. The key thing, though, is the way that people are using that data right now, I think, is a little silly. It's basically taking that data, filtering out only the really, really good stuff, plugging that into the base model and saying, learn to memorize like really good things. But all the bad things that you saw, or all the random stuff even that you saw during eval, you should be using too. Shove that into your world model and start to do reasoning there. So that's kind of the philosophy I think I'm taking.
Technical follow-up is like, it seems like the sim-trial gap for learning L theta is not that large. Have you thought about using sim-trial method to learn safety specifications? Like you can label everything you want in simulator, right? Maybe pre-train simulation, finding the real world, this kind of thing?
Yeah, we discussed it, but RSS was 2 weeks ago.
Thanks.
Yeah,
that's
no
all the question I have.
How big was your data set for your training model?
Yeah, so for the Skittles, it's 1,300 demos. 1,000 of those are random. So my student just got the robot to bumble around. 150 of those were explicit successful demos. 150 were explicitly unsafe. But you can see the details in the paper. Yeah. I'm going to go to this side. Yes.
I was thinking about how you would apply this to a real-time system kind of in the open world. How fast was the evaluation in the human shielding example? How often was it doing the shielding evaluation, and how fast does it run?
Oh, yeah. So the videos were all real time. Ken is in the background. Ken, do you know off the top of your head what the frequency was of the filter?
I think like 10 or 15 hertz, somewhere around there.
The VLM is a little slower. So we benchmarked each of the components of the pipeline in the paper that you can check out. Our VLM system takes about 2 seconds to do the reasoning, which is, by the way, much better than the VLM Act baseline, the end-to-end model. That one's like 22 seconds or something. So there's still much more improvements to be made on the real-time nature of this. Yeah.
Where do your safety controllers come from? Are they just blocking the inputs? Do they actually attempt some kind of recovery behavior?
Recovery.
And is that recovery behavior learned via like RL given your safety set?
Correct.
Okay. And that works like out of the box, you can, or not out of the box, but like with your existing data set, you can learn those recovery behaviors from well. That's pretty cool.
Yeah. I am so validated. Highest praise ever. All right, you were next.
Thanks for the great talk. A lot of the examples, at least, you've shown, I don't know if it's in the theoretical part or not, but have a very clear kind of like binary classification between success and failure. How does this kind of framework, especially in the latent space, like extend to things where there's like uncertainty around risk or like relative amounts of risk or like where you're thrown into an unsafe situation and where one situation is slightly less unsafe than another, like when you're driving, like how does that?
Yeah, good question. Maybe my 2 answers to this is one, I have a PhD student, June 1, he's going to solve the uncertainty part of that. So stay tuned. We have some work thinking about what uncertainty means in these models and how we can think about safety in that context. Your other point about things that maybe aren't hard boundaries, there I would definitely look at the offline RL community, which we are very much inspired by and building off of. And there, if you think about a general reward function, right, that you're just looking at some sum over rewards over time, you could definitely use. But the way in which you actually encode something maybe a little bit softer, you could do via maybe a risk metric as well. So for example, if you read the first paper I talked about, technically, you see we have like an expectation over the generated latent states, which hardcore safety people get really stressed out about those expectations. Technically, you could put another measure there too. You could do something like CVAR or whatever. But yeah, I think that's an interesting frontier, to be honest. I'm trying to remember who was next. Sure.
So what, if you're stuffing it all into the latent space, what happens if you have multiple different modes for failure?
Multiple different modes for,
so
can you give me an example? Yeah.
If you have just like failure and not failure, you can measure like distance, there's a distance, there's a metric, right, for staying away from failure. Now, if you have different failure modes, different ways that you could fail. So like it falls out of the bag, there's one failure mode, or like, so multiple different modes that you could fail, and like how you resolve that in the latent space, and then things like, like dynamic, like a bifurcation. Right, like your safety mode changes as a function of state or time.
Yeah, so we can talk about technical details if you want offline, but in theory, the safety specification does not have to be convex. So you could have, I drew just like one little bubble there, but you could have like, like a polka dot pattern in your latent space that you're trying to avoid. That's all fine. You're reasoning about all of them simultaneously during optimization.
How do you know the closeness of the polka dots that are in the latent space?
So maybe one low-level technical detail here is that the L of X function we learn in latent space is not actually a proper metric. It's just a classifier. If you want a proper metric, we can work together. Figure that out. Yes?
Yeah, thanks for the great work. I think it's really nice to abstract the state space to like image and latent, and abstract the humans label to like a classifier. My question is, for example, in the Skittle example, I think, for example, for the bag, which side is cut open is also important, right? And if say we see the gripper grabs the Skittle bag, if I cut the other side, then it will be opposite in terms of safety constraint. Yeah. So I think maybe definitely it works for. One example is super great, but I just wonder how do you consider involving different factors into the latent space?
I love this question. If I'm being very honest, I don't think we know yet as a community how these particular types of models would necessarily handle that. The way I like to think of it from a first principles perspective is all about observability. So if I have a bunch of data where I've seen bags that are open on this end, and as long as I can kind of infer them from a sequence of measurements, like I can infer which hole is open, I think my safety control should work. Whether or not something is observable is a separate question, and whether or not you have data coverage about that is another question.
Just a very quick follow-up.
Yeah.
I think one I'm maybe naive, is if the graper has a force sensor, when we drag it around, we can measure the force or torque.
Exactly. So there's a lot of really exciting things about like multimodal world models too, and this is a great point. Yep. Thank you. I think in the back was waiting. Yeah, go ahead.
Great talk. I think I was very excited about how you were generalizing the notion of safety from just collision avoidance to general safety. And I'm thinking there are two extremes. One is that you rely solely on pre-trained models, pre-trained world models, like if Sora actually worked, maybe you're a better version of Sora, and Gemini and so on for detecting failures and so on, without using any interaction data. And the other extreme is you actually use interaction data to find out the safety critical things and so on, but then maybe it won't generalize, maybe we don't have enough data of how things fail, and there are corner cases and so on. So where are you thinking, let's say in 2 years or 3 years, where are we going?
Maybe I'll pick on just one thing that you said, which is that I don't think that video generation is the way to go. I don't, because think about this, right? What you're doing is you're forcing the video generation model. It's learning inside some representation, right? But then it's decoding into all of these images. First of all, that's really, really time consuming. It's super slow to do video generation and then pass that to the downstream model. The other thing that you're skirting is the need for eventually doing some state estimation down the line. Whoever consumes the videos themselves is going to have to infer the state again. So it's kind of weird. It's like you're basically saying, oh, that's not my problem. As long as I give you a really beautiful video, okay, the control people or the planning people will figure it out. What you should really do is you should think about constructing from that data itself a sufficient statistic of the world and then do reasoning directly on that. No need to do this extra decoding stuff. This is my philosophical take. This is why we take this particular approach. However, it is true that when people, like when you guys go talk to your industry friends or whatever, they'll oftentimes say that a video prediction model is a world model. There's an interesting paper actually that recently came out that says that may or may not be the case. So, but we can get into philosophy later, maybe during the PSR or something. I'm trying to figure out who was next. I think you were waiting for a while.
So when you were showing the LLM deciding is this safe or not, I was kind of thinking of the sentences it was producing. I could write down a propositional logic statement that was that.
Yeah.
So have you thought at all about just using the LLM as a translator from human to propositional logic to PDDL planner and then back up?
Yeah, we've talked a little bit with some other folks who come more from like the signal temporal logic or domains kind of related to this. We haven't done this ourselves. I think it's a very cool frontier. Yeah. Yes.
Have you thought about some ways of identifying the causality of these failures in some way?
No, but if you want to work on that. Yes.
It seems to me that when you're trying to define I agree that open world robot safety is very hard, but it seems that the difficulty most comes from pixel.
From what?
Pixel.
What do you mean by the difficulty comes from pixels?
Because if we have everything in simulator, for example, for the Skittle example, I think we have perfect state estimation of every particle.
Okay, but then why is sim-to-real still a problem?
Sim-to-real is a problem, but I think the problem majorly comes from how do we do state estimation from pixel to infer those stuff. Have you ever tried just directly use your method on state-based instead of pixel-based?
But if I have a state, there's no need for me to do the encoding anymore. I just am going to do some dynamics model fitting on some low dimension state. Yeah. My argument also though is that even if you had a perfect simulator, I still think the state representation isn't trivial. Remember that liquid spilling I was showing you? Let's just go back to that slide deck. To be totally frank also, Ken tried to set up an Isaac Jim simulator for wine spilling. He tried really hard. Not only is this slow to simulate, but again, what is the state of this? Yeah, that's why the pixel-based methods is kind of how we started thinking about the problem. Yeah.
During Ken's tether operation, is there any failure case that he successfully spilled everything out?
Oh yeah, I mean, we have not verified, for example, the safety value function itself to say that, with probability 0, it will always, with probability 0, it will, never cause a failure. If you go to the project website, you'll see, I should have included it in the talk, you'll see a scenario where one skittle pops out. Okay. So it happens. Okay, Zeynep, you're the boss. What else?
You are the boss. Thank you very much.